Hello everyone, welcome to our this inorganic session. This is subject CHR 230 Coordination Chemistry, section first, and this is our fourth lecture about microstates and term symbols. So we will discuss about microstate or what is terms and term symbols. Okay, just we will discuss about optical absorption spectra, also called electronic spectra of coordination compounds. So, we have previously argued that ligand field theory can predict and explain the electronic spectra. Only in few relative cases, ligand field theory means LFT, that is ligand field theory, is sufficient to explain the spectra. For example, hexaquanickel 2 plus complex or 2 plus complex ion, which is in octahedral filled or D8 complex, because there is 8 electrons in Ni nickel, because nickel is having plus 2 oxidation state. That's why this system is D8 system, or the complex is D8 complex ion. Our complex is hexaquanickel 2 plus complex and nickel D8 system. Okay, so according to ligand field theory, the metal d orbital in an octahedral field are the T2G and EG orbital. There are T2G and EG orbital, or T2G or EG sets. Okay, so 6 electrons are in the T2G orbital and 2 electrons are in the EG orbital. There are 8 electrons in nickel or Ni2 plus nickel atom, and out of that 8 electrons, 6 electrons are in the T2G orbital and 2 electrons are in the EG set, because T2G level is ground level in octahedral case. Ligand field theory would predict there is one electron transition possible, namely the promotion of electron from a T2G into an EG orbital, means ground level T2G into an EG orbital. Okay, but this process would be triggered by the absorption of light. Light absorption or light is required for this process, whereby the wavelength of the light would depend on the delta O. What is delta O? That delta O is magnitude of octahedral field, or the splitting in octahedral field. So that wavelength, it is depends on the light or the absorbed light, and light would depend on the delta O or delta octahedral between the T2G and EG orbitals, means two different energy sets like T2G and EG orbitals. Overall, this should lead to a single absorption band in the absorption spectrum of the complex. It shows single absorption band in the absorption spectrum of the complex. So we can check this prediction by experimentally, and here it is different absorption patterns or absorption bands. So in this picture we can see two orbitals or two sets of orbitals like EG and T2G. Okay. The absorption spectrum is far more complex. Actually, CFT shows this absorption spectrum. So this absorption spectrum is more complex than we expect. Instead of just a single absorption band, there are multiple absorptions are there. Not only single absorption band is there, there are multiple absorption bands we can see. Ligand field theory is explain the spectrum. There are multiple absorption takes place, and that ligand field theory is not able to explain all these spectrums. LFT means ligand field theory assumes that there are no electron-electron interaction. Ligand field theory or LFT said that there are no electron-electron interaction. However, in reality, there is repulsion between the electrons in d orbital, and this has an effect on their energy. So today we will discuss about effect of electron-electron interaction. or as we see, there is a repulsion between between electrons in d orbitals. So let us discuss effects of electron-electron interaction. What is electron-electron interaction? Let us look closer at this picture. There is splitting pattern, like there are two energy sets, Eg and T2G. Let us consider D2 ion in an octahedral ligand field. Okay, so D2 means it is D2 system in an octahedral field, means there are only 2 electrons in that metal. Okay, so there are 2 electrons, and 2 electrons in an octahedral ligand field. That system is exposed in an octahedral ligand field. Okay, so according to ligand field theory, there are 2 electrons would be in the T2G orbital. Okay, look at this first picture. There are 2 electrons would be in the T2G orbitals when the ground state. Before excitation or in ground state, 2 electrons would be in the T2G orbitals. They could be in the XY, XZ orbitals, and this XY and XZ orbital, or the position of that electrons in XY and XZ orbitals, is called a microstate. There are different arrangements of electrons, not ligands. There are different types of arrangement of electrons. So these all arrangements of that electrons in different orbitals are called microstates, suborbitals. Okay, so it is called a microstate of a state because there are other combinations of orbitals are also possible. For example, the ground state would also be realized if 2 electrons were in the XZ and YZ orbitals. If 2 electrons are in the XZ and YZ orbital, there are 3 orbitals, XZ, XY and YZ. But the ground state would also be realized if the 2 electrons were in the XZ and YZ orbitals. So this combination would be another microstate associated with the ground state electronic configuration or electron configuration. Upon excitation using light or electromagnetic radiations, the electron in the dxy orbital could be promoted into an Eg orbital or excited Et orbital. After absorbing light energy, the electrons in the dx, all these orbitals are d orbitals, so electrons in the dxy orbital could be promoted into Eg orbital or excited energy level. So which could be either the dz square or dx square minus y square. There are two orbitals are there in Eg state. So these two orbitals are dz square and dx square minus y square. So that electron, which is electron in dxy orbital, could be promoted into an Eg orbital. That electron could be either in the dz square or dx square minus y square. So those two possibilities reflect to different microstate associated with the excited state. So let us assume the electron goes into the dz square orbital. Okay, that electron goes to dz square orbital, and in this microstate one electron would be in the dz orbital and the other one in the dz square orbital. So in this condition, or in this arrangement, or arrangement is nothing but a microstate. So in this microstate, one electron would be in the dz orbital and the other excited electron in the dz square orbital. Now there are another possibility how to excite an electron. We could assume that the dxy electron is promoted into dz square orbital, but the dxz electron gets promoted. In this case, we would realize a microstate in which one electron in dxy orbital and the other one in the dz square orbital. So one is dxy and other one is a dz square orbital. Okay, so there are two different orbitals, or these two electrons are in two different orbitals. Now let us compare these two cases. Ligand field theory would argue that both excited microstates have the same energy. Ligand field theory said argued that both excited microstates have the same energy. Okay, which two excited states? There are possibilities of two excited states. First one, the electron excited from dxy orbital and promoted to dz square orbital, and another possibility is the electron from xz orbital, and after absorbing electromagnetic radiation, that electron gets promoted into dz square orbital. So there are two different orbitals like dxy and dxz, and at ground state electron are present in dxy and dxz orbitals. Okay, so that is because the electrons in two excited microstate interacts differently. Okay, and ligand field theory would argue that both excited microstates have the same energy, like xy to dxy to dxz and dxz to dz square. Okay, so in fact they don't have same energy, because the electron in two excited microstates interact differently. In first picture we can see electron in dxz, ground state electron in dxy gets excited, absorbs electromagnetic radiation and promoted to dz square. And in second case, or in second figure, we can see electron, there are two electrons in T2G orbital. Okay, so second electron which is present in dxz, okay, that electron also absorbs electromagnetic radiation and promoted to dz square. So there is difference in environment. First electron from ground state, the ground state of first electron is dxy and the ground state of another one electron is dxz. So that xy and xz are different, and that electron promoted to same orbital like dz square. And this is because of, this becomes possible when considering the orbital shape. Okay, the dxz orbital has electron density on z axis, that first orbital like dxz, the dxz orbital has electrons or electron density on the z axis, while dxy orbital has not, that dxy orbital don't have electron density on z axis. Therefore, electron in these orbitals would be expected to interact differently. That's why these two electrons having different energies, or they require different energies or interact differently with an electron in dz square, that with an electron which is excited state is same. So orbital which has most of its electron density on the z axis, in this orbital dz square, that orbital which has most of its energy, most of its electron density, not energy, most of its electron density on the z axis. As a result, the two excited microstates do not have the same energy, because one electron is from dxy and second electrons is from dxz orbital. Okay, that's why the two excited microstates do not have the same energy, and this means that in order to promote the electron into two different microstates, we need different amount of energy. Okay, thus the complex would absorb light with more than just one wavelength. That is why the complex absorbs light with more than just one wavelength, and this is in contrast to what ligand field theory predicts. Ligand field theory argue that both excited microstates have the same, but in this case, this is contrast what ligand field theory predicts, and these two electrons shows two different electron requires different energy. Okay, so what will we need to do in order to correctly predict how many absorption bands we get? The answer is, we must find all possible microstates for this D2 system and electronic configuration, and group those together which have the same energy. So a group of microstates with the same energy is called a term. There are two different microstates or two sets of energies are microstates, but a group of a microstates with the same energy is called a term, and the number of electron transition can then be predicted from the number of terms. Okay, so this is a pattern of transition. So in this second figure we can see there are two different orbitals, and in these two different orbitals the energy of that dxz and dyz, then dxz, dyz and dxz is different. That is why it shows two different microstates. There are three different orbitals in T2G set: dxz, dyz and dxz, dyz and dxy. So these three orbitals are there, and these three orbitals having different energy because the shapes of that orbitals are different. Okay. Now we will discuss about microstate. So what is microstate or meaning of microstate? Okay, the number of microstates means n of a system corresponds to the total number of distinct arrangement for e number of electrons to be placed in n number of possible orbital positions. Microstate is just an arrangement of energy states or electronic or arrangements of electrons in different orbitals, different arrangements or possibility of electrons or different arrangements of electrons are nothing but the microstates. Okay, so what is microstate and how to calculate microstate? There is a formula. We can use that formula to calculate the microstate. So microstate is equal to capital N factorial. What is capital N? The number of microstate, that n, microstate n of a system, that capital N factorial divided by n small n factorial into bracket capital N factorial minus small n factorial. Okay, so this capital N means the capacity of orbital to carry the electron. If orbital is s, so s orbital having capacity to carry 2 electrons. If orbital is p, then that p orbital having capacity to carry 6 electrons. Okay, so n factorial, this capital N stands for the capacity of orbital to carry how many number of electrons. That small n means the number of electrons which are present in that orbital. Like if system is D2 system or DH system, means there are 2 electrons in that central metal, outermost or valence electrons which are present in that central metal. So that n factorial or small n is how many electrons are there. Okay, so we can use this formula to calculate the microstates. So n is equal to capacity of orbital and small n is equal to number of electrons present in an orbital. If system is D7 system, then small n is equal to 7, and orbital is D, then capacity of orbital is 10 electrons. That D orbital having, there are 5 D orbitals, that's why the capacity of that orbital to carry 10 electron. Okay, so of overall microstate in terms is equal to 2L plus 1 into 2S plus 1. So calculate the number of possible electrons or arrangements in the given configuration. So there are different arrangements of electrons in given configurations are different microstates. So all these are number of microstates. So these electrons can arrange differently or in different ways or number of ways. That number of ways are nothing but the microstates of that electrons. So there are 6 factorial divided by 4 factorial, 2 factorial is equal to 50 microstates expected. Okay, so these are microstates. In this case there are it is actually p orbital, and at p orbital this case is p2. There are 2 electrons, means small n is equal to 2, and p orbitals having capacity to carry 6 electrons. But we can see in this picture there are the different arrangements of electrons in that subshells of orbital. So there are 3, we can draw 3 orbitals. First orbital is +1, second orbital is 0, and third orbital is -1. Okay, so ml and ms value. So we already have studied about quantum numbers like ml and ms, means spin quantum number, and L means orbital quantum number or azimuthal quantum number. So we know that what is quantum number. So in this orbital we can arrange 2 electron in different ways. There are how many ways? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. We can arrange these 2 electrons in 3 subshells of p orbital in 15 different ways. Okay, like this. In first case, we can put 2 electrons, first electron in +1 orbital, +1 subshell, and second electron in 0 shell. In second case, we put first electron in +1 subshell and second electron in third subshell, that is having -1 value. Okay, -1 ml value. So like this we can arrange that 2 electrons in p orbital, or there are 3 subshells of p orbital in 15 different ways. Okay, so that 15 is microstate of that system. That system is p2 system, because this is p orbital and having 2 electrons. So for p2 system, the number of microstate, or in p orbital we can arrange 2 electrons in 15 different ways. That's why that 15 is number of microstates. Okay, now there are some problems or some examples how to calculate microstates in different systems. Okay, so we can use this formula like n factorial, capital N factorial divided by small n factorial into bracket capital N factorial minus small n factorial. Question number 1 or problem number 1 like this: for ns1 configuration, n is any number. For ns1 configuration, number of microstates is equal to, what is ns1? ns1 means this is s orbital having only 1 electron. So n is number of orbitals. So ns1 configuration, what is capacity of s orbital to carry electron? S orbital can carry only 2 electrons. So total capacity to carry electron is 2. That's why 2 factorial, that's capital N. What is exactly capital N? As we already have discussed, like n is equal to capacity of orbital. Capital N is equal to capacity of orbital, and small n is equal to number of electrons present in that orbital. Okay, so in this case, the case is S1 or S1 configuration. The capacity of orbital is 2, means capital N is 2, and small n is, there is ns1, means only ns1, that 1 is equal to only 1 electron. So there is 1 electron in s orbital. Okay, so capital N is equal to 2 and small n is equal to 1. So put that value in this formula. The formula is n factorial divided by small n factorial into bracket n factorial minus n factorial, small n factorial. Okay, so 2 factorial divided by 1 factorial into bracket capital N is equal to 2. That's why 2 factorial minus small n is equal to 1, because there is only 1 electron in S1 system. That's why minus 1 factorial. So solve this problem like 2, it is just a simple problem. 2 into 1, like factors, like 2 into 1 divided by 1, the 2 minus 1 is equal to 1, that's why it is 1 factorial into 1 factorial. It is 2 into 1 is 2 divided by 1 is 2. So the microstate of that ns1 configuration is 2. The final answer is 2. Means there is 1 electron in s orbital, and we can arrange that 1 electrons in 2 different ways, or there are 2 different arrangements of that 1 electron in s orbital. That's why that is why the microstate is 2. There are 2 arrangements, that is 2 arrangements is nothing but the microstate. Okay, so just go for second case. The second problem is for NP1 configuration, number of microstates is equal to What is np1? N is any number. P means this is p orbital, and p1 means there is one electron in that orbital. So capacity of p orbital is to carry 6 electron. That's why n, capital N, is equal to 6, and p1 means only one electron is present in that orbital. That's why small n is equal to 1. Okay, so capital N is equal to 6 and small n is equal to 1. That put that value in that formula. Then 6 factorial divided by 1 factorial into bracket 6 factorial minus 1 factorial. Okay, then factors are there. 6 into 5 into 4 into 3 into 2 into 1 divided by 1 factorial into bracket 6 minus 1 is equal to 5. So start from 5 factorial, 5 into 4 into 3 into 2 into 1. Okay, so final answer is 6, means number of microstate for np1 configuration is 6, means in p orbital, if there is one electron is present in p orbital, so that one electron, that single electron, we can arrange in 6 different ways, or there are 6 different arrangement of that single electron in p orbital is possible. So that 6 different ways or 6 arrangements are the microstates of np1 configuration. Okay, so this is very simple problem. Then go for third problem. That third problem is system is ND1 configuration. The configuration is ND1. Like these two problems, solve this one also. That ND1 is d system, d orbital. D orbital, capacity of d orbital is, there are 5 d orbitals and capacity is each orbital carries 2 electrons. That's why the total capacity of d orbital is equal to 10, and number of microstates is equal to that 10 factorial. Only one electron is there which is present in d orbital, and that one electron can arrange 10 different ways. That is why the microstate, by the calculation, the final answer is 10 by the factors, or by calculation the final answer is 10. That's why we can say one electron which are present in d orbital can arrange 10 different ways. Okay, or the arrangements are 10 arrangements. We can see 10 arrangements of that electron in d orbital. Okay, so microstate of ND1 configuration is D. Same, calculate the microstate for NF1. The capacity of f orbital, there are 7 f orbitals, each orbital carries 2 electrons. That's why the capacity of f orbital is 14 electron. 14 electron can carries f orbital can carries 14 electrons, and that's why the capacity of NF1 orbital is 14. So capital N is equal to 14 and small n is equal to, there is only one electron in f orbital, and that electron, we can arrange that single electron in f orbital in 14 different ways, or there are 14 possibilities to arrange the electron in differently, or 14 arrangements we can see in that NF1 configuration. That is why NF1 configuration, or the microstate number of that NF1 configuration is 14. Okay, now there is this is another one problem which is little bit different. There are 2 different orbitals like 2s1 and 2p1 configuration. So calculate the number of microstate. So we can calculate 2 different orbitals, or the microstates of the 2 orbitals separately, like 2s1 and 2p2. Okay, and then multiply these two orbitals, then you will get final answer like this. In first case, there is 2s1 configuration and another one configuration is 2p2 configuration. So what is 2s1? In s orbital, only one electron. So capacity of s orbital is 2. That's why n is equal to 2, and there is one electron. That is why small n is equal to 1. So here in this formula, n factorial, capital N factorial divided by small n factorial into bracket capital N minus small n factorial. So there is 2 factorial divided by 1 factorial into 2 factorial minus 1 factorial. So answer is 2. And in another case, there is 2p2 configuration, means p orbital having capacity to carry 6 electron. The total capacity of that orbital is 6. That is why capital N is equal to 6 and small n is equal to, there are 2p2 configuration, means there are 2 electrons in that p orbital. So small n is equal to 2. So 6 factorial divided by 2 factorial into bracket 6 factorial minus 2 factorial. That is why 6 factorial means 6 into 5 into 4 into 3 into 2 into 1, and divided by 2 factorial means 2 into 1 into bracket 6 minus 2 is equal to 4. So make some factors like 4 into 3 into 2 into 1. Then final answer is 15. Now for first orbital 2s1 number of microstates are 2, and for second orbital number of microstates for 2p2 number of microstates are 15, or in or we can arrange 2 electrons in p orbital by 15 ways, or by there are 15 different arrangements of 2 electrons in p orbital. That is why 2 into 15 is equal to 30. So number of microstate for 2s1 and 2p2 configuration is 30. So we can arrange 1 electron in 2s1 and 2 electron in 2p2 configuration mixed in 30 different ways. That is why the number of microstate for 2s1 and 2p2 configuration is equal to 30. Okay. So now by using this method we can calculate the microstates of different configurations. It is very simple question. So okay, you can try to solve different configurations and microstate problems. Okay. Now in our next chapter or in our next lecture we will discuss Russell Sounder term or term symbol. Okay, thank you.